Okay, now, here's one that's a little unique, okay? So what's happening in this, I'm actually going to go back a few slides and then I'll hit this back up. If you look at going back to this particular case, a W section connected via the flanges, this is a very, very common connection for tensile elements. The way that we handle shear lag is when we say, all right, when I take this member and I kind of yank on it, would a fair way of looking at it be that about half that load goes to the upper part of the member and half that load goes to the lower part? Is that a fair way of looking at it? Make sense? Okay. Well, when we have this particular situation right here, okay, where we have a W section that is connected via the flanges, to get our connection eccentricity, instead of looking it up in the W section or the W shapes, we look up the centroid from the equivalent WT. So let me explain what I mean by equivalent WT. So here's my original section, right? Okay, so original section. Samurai sword or lightsaber, I cut it in half. Okay, let's go back to this right here, W12 by 30. Remind me, what's the 12 mean? It's about how deep it is. It's nominal depth. What's the 30 mean? Pounds per foot, how heavy it is. So this is about how deep it is. This is about how heavy it is. Well, if I cut this thing in half, what's going to happen? The depth is going to get cut in half, right? And the weight's going to get cut in half. So here's what I would do. If I've got this particular connection, and again, this is a unique snowflake. We're only talking about this particular type of connection. If I've got, let's say, a W12 by 30, I would go to the WT shapes, and I would find the WT 6 by 15, and then looking at the WT 6 by 15, I would look up the centroid, which we're talking about this centroid up and down from this connected face to this centroid, so I would look up Y bar, okay? So if I've got a W12 by 30 connected via the flanges, what would the connection eccentricity be? Let's pop quiz everybody. 1.27. Let me see if I can. What's that? 1.27. That is correct. All right. No. I'm done. I'm done. I'm done.
Is there going to be cases when there's not like something completely divisible by 2?
Yeah. If you're talking about a channel or an angle or something like that, you wouldn't do this. This is only for like I-shaped sections, like W shapes, M shapes, HP shapes, S shapes, only those. Okay. If you're dealing with a channel, you would just look up the centroid, directly from the channel or something like that.
Dan, what if,
Yeah, I think he's saying, like, is there a situation where you're not going to have an equivalent
like I have a 16 by
WT
31 here, 31 divided by 2, something like that.
They do. For every W, no, that's a good question. For every W shape, there should be an equivalent WT, and there are, like 15.5s. It should be listed. You see it? No, that's fine. That's fine. I mean, so yeah, find an equivalent shape. But if you just look through the WTs, you should see like 0.5s or something. Yeah. There you go. Yeah. Yeah. Just remember, in design mode, the W14 by 800, it will work. It will always work. It won't be the most economical, but it will work. Okay. Sound good? Okay. That's the connection eccentricity. Here's the length. The length is literally the distance from out to out from your bolts. So from, the outermost bolt on the left to the outermost bolt on the right, whatever that length is, that's your connection length. And the idea is that the longer that connection length is, the longer that length is, the more room those stresses have to permeate throughout the cross-section. Remember, when we samurai sword or lightsaber, we're doing that through the lead line, right? So for this upper connection that's right here, for this lower connection right here, the one that's all the way over here. Look at the difference between this connection and this connection. This one has a longer connection length, so those stresses have had more room to propagate. In other words, more of the section is effective, right? Remember, we take net area times U to get the effective net area, right? Make sense? So longer connection length, larger shear lag factor. Look at what the equation does. 1 minus x bar divided by L. That L gets larger and larger. 1 minus x over L gets larger as well. Make sense? Okay. Now, if you've got a staggered connection, again, exterior bolt to exterior bolt, okay? So just literally the bolt that is all the way over here to the bolt that's all the way over there. However far that distance is, that's your connection length. Sound good? Yes, sir.
Can shear lag factors be negative? Like if the
No.
okay, so L's always going to be larger than X bar.
Yeah. The centroids that we're talking about are, tiny. We're talking about 1 to 2 inches. You will never have a negative shear lag factor. I see what you're saying, that mathematically it's possible, but for that to happen, you would have to have a really, really massive member with a little itty bitty connection, and you never do. No, that's mathematically I see what you're talking about, but in terms of applying that to a real world situation, that would never happen. That's a good question, though. All right, sound good? Okay. All right. If you've got welded connections, you would take the connection length as just the average length. So, for instance, if you're talking about, like, if you have an angle and it's only welded on the longitudinal lens, that's L. Even if you've got a transverse weld, that's L. If you have what's called a balanced connection, which we'll do that later on when we talk about welded connections, just take the average. So if this is 2 and that's 6, then take your length to be 4. And if you're wondering why you do that, well, we place more weld over here because the centroid is closer to this side. We do that to try and eliminate as much bending in the angle as possible. So since the centroid is closer to that end, we throw more weld in to try and balance the equilibrium out a little bit. Does that make sense? We'll get to that later. Don't worry. We will design connections like that